Hello, and welcome back to the Dark Reading News Desk. I'm Becky Bracken, editor with Dark Reading, and I am here to welcome a very exciting guest to the desk, Daniel Moghimi, a senior research scientist at Google, who is presenting what is truly blockbuster research on a vulnerability he's dubbed Downfall. It's a bug in billions of Intel CPUs, revealing a major design flaw. Welcome, Daniel. Can you tell us a little bit about how you started looking at these Intel chips?
Yeah, of course. It's not the first time I report this kind of vulnerabilities to Intel, and I've been doing this kind of research, looking into to the microarchitecture and the underlying things that happens inside the CPU that not a lot of people look day to day. And last summer, I came across this particular optimization that Intel has introduced probably about 15 years ago into the CPUs that helps software to speed up memory accesses and access data a lot faster than normal. And based on some analysis and looking into how this instruction is optimized, I had an intuition that it could have similar vulnerabilities to the past, like meltdown and microarchitectural data sampling. So then I started, writing some test code and running it in a few different CPUs, and it turns out that my hypothesis that this kind of instruction would have this kind of vulnerability was correct, and then I reported this to Intel last summer.
Okay, so you find downfall and you realize this is a pretty widespread issue. Can you walk us through what an attacker could potentially do with this vulnerability?
Yeah, so the vulnerability enabled an attacker to leak data from the hardware register file that's normally not accessible to the software. So when people build a CPU, there are lots of components inside the CPU that nobody even knows about them. It's just the software execute instructions. So you have these things like software registers, and you essentially don't have access to that hardware component. But this vulnerability essentially violates that boundary of software and hardware. So an attacker can leak data from that hardware register. And once you violate that boundary, you can do all sorts of different attacks, stealing data from other users in the cloud, steal data from other applications in a desktop computer, on a laptop computer, or even, for example, if you download an app from a marketplace on your Windows PC or in your MacBook that runs an Intel CPU, these apps generally are supposed to be confined and not access your photos, not access your bank.
Right.
But essentially, this vulnerability enables an attacker to access those data that you're not supposed to.
How difficult is this? Is this a highly technical exploit to pull off? Is this something that your run-of-the-mill threat actor could get done?
It could be hard to find these kind of issues, but once you find it and once the information is out, it's actually very easy to exploit it. In fact, when I shared this paper I wrote with one of my colleagues at Google, he could reproduce the attack in less than a week, like as somebody who is technical. So there are a lot of people out there that now that the information is out, they can reproduce this kind of attacks, and it's highly practical. It takes some time to make specific exploits to target different credentials, because the attack I demonstrated, you can steal encryption keys from OpenSSL, but imagine if you want to steal other sort of information, you have to spend probably a couple of weeks customizing your exploit for that.
So I take it there haven't been exploits in the wild that you've been able to observe yet, or have there?
There have not been, and I'm not in a place to know if there are such things. Generally, these kind of attacks probably are, if it happens, it's more targeted. It's rare that somebody tries to exploit a lot of people with these kind of attacks. But I'm also hoping that would not happen. There are lots of places that this kind of thing can impact users, and I'm hoping that we have managed to patch and fix enough computers since Intel released this that this kind of thing won't happen.
So what was the process like with Intel? You reported last summer, you said, and what was their initial response? Tell me more.
Well, I mean, their initial response after, I think, a week or two, they managed to reproduce it. They have a triage team in their site that they check if the report is correct. they were in a big surprise because they have invested a lot of, I can imagine, resources in the past few years to handle this kind of issues after meltdown and microarchitectural data sampling. And it was known for a lot of people, even for Intel, that they have fixed this issue, so they're not going to invest more time in this kind of problem. So it was really shocking for them, but once they saw that it's working, then they asked for an embargo time for August this year time. And in the meantime, I continued writing my research paper.
And so they've issued patches, and so there's enough confidence that there's enough mitigation there to make this sort of a non-starter.
So the mitigation Intel has released for this is a microcode fix. That microcode is this special firmware that runs into the CPU core that modifies the behavior of this optimization. And this microcode fix, from my understanding, it solves the issue at the moment. So we don't know if there are any other instance of these problems that's going to happen. But right now we know that the microcode fix works. And the microcode fix is distributed to cloud vendors, to customers, and eventually it's going to land in different operating systems and OEM vendors. It may take some time, maybe for another month or so, for everybody to really have everything patched, but I'm just encouraging everybody to just ask their OEMs and providers to get this patched. There are some consequences. There are some performance overhead according to Intel. Some workloads may get affected up to 50% overhead. So that's a challenging thing for some customers, I can imagine. But I would say it's worth paying for the security.
Yeah, that is an interesting calculation that they're going to have to make. So where we stand now, you are going to, you've submitted your research, the mitigation. Are you going to stay on this sort of path of researching these CPUs and Intel in particular?
I'm a hardware security researcher, and I continue to look into the security of computers, CPU and processors, and I will continue looking into both x86 and ARM and other CPUs as well. So you can imagine maybe I'll look into Intel CPUs again too.
Sure. So that it's so many times throughout your explanation, you said nobody's really looking at this. I'm one of the few people that are looking at this. Why not? If there's a billion CPUs that could be affected, I would think that, is it a lack of expertise? Is it a lack of knowledge that hardware, software, membrane is more vulnerable than we think? Why is this not more top of mind, considering the footprint that it casts?
I think there are a few factors. Well, one is that the whole research around microarchitectural attacks being taken more seriously started in 2018 with meltdown. So it's been only 5 years that there are people who are getting educated and learning to do this kind of research. But I'm sure there will be more, and we'll see more of this. The other guess I have is that as it's getting harder to exploit software, people are going to look into exploiting hardware more. So we are going through that transition probably in my generation, that people are looking into hardware more. So right now maybe there are I don't know, these research teams spread across academia and industry who are looking into this problem, but I think we can imagine seeing more people even who look into this problem in the future.
Can you tell us what some of the top hardware vectors are? We just have a couple minutes, but I'm interested to hear, as hardware attacks come up beyond CPUs, where else should we be looking?
Well, I can imagine right now we are in this period also in the computer architecture world that we are reaching the end of getting free computation. You may have heard that Moore's law is slowing down, or it's ending. And the idea is that we're going to build a lot of different accelerators and optimize them in different way and put them on the same chip to make computation faster. That could include AI processors, GPUs, and all sorts of digital signal processor and things like that. And all those things could have the same vulnerabilities. It's just people have not looked at them as much.
Well, the good news is you will not be bored in your work, it looks like. Daniel, thank you so much for joining us. Can you tell our audience where they can find out more about your research?
Of course. So I put a website up called downfall.page. That includes a Q&A, some demo on this exploit, a link to proof of concepts, and also a link to the paper for more technical details.
Excellent. And did you come up with the name Downfall? It's quite good.
Yes.
It's really good. So, congratulations.
I mean, if you have tracked these kind of issues, there was meltdown, and then there was fallout, and downfall is like it's making a sequel here.
I just thought it was a good word choice, honestly. Daniel, thank you so much for joining us at the Dark Reading News Desk. We very much appreciate your time.
Thank you.
Thank you.